Hi, I'm Nima. I'm currently a postdoc at the Max Planck Institute in Bonn. Before I start, I want to thank the organizers for giving me this opportunity, and I want to thank you for watching this, and I hope you enjoy this talk. Alright, before I start, let me make two comments. First of all, the slides for this talk are available on my website. You can also find it using this QR code. Also, I currently have three overarching projects that I'm working on. The first one focuses on understanding infinity n categories, and in particular limits therein. And this is joined with Lim Moser and Martina Rovelli. And the second one focuses on understanding and developing a homotopy invariant foundation. And the last one studies homotopy coherent properties of Hochschild homology, and that is joined with Catherine Hess. In the interest of time, I'm going to focus on the second project for this talk, but if there is an interest, I'm happy to discuss the first and third and answer any questions about them as well. So, in order to motivate the need to understand kind of mathematical foundations for homotopy theory, I will kind of illustrate by reviewing the development of algebraic topology. And what I'm going to say is, of course, a crude approximation to the real thing, but I think it will illustrate my point. So usually when we try to do algebraic topology, we start with some kind of building block, like some kind of homotopy type, like a topological space, or if we do sheaf theory, a locale. And then we develop some kind of computational invariants, like a homotopy group or a cohomology group. And then we develop like a very advanced theory, right? Like a homotopical algebra, stable homotopy theory, and so on. And I would say there's something that underlies all of these developments that comes in some sense before all of those, namely a set. In order to understand what a topological space or Kahn complex is, I need to know what a set is. And that suggests following reasonable questions, right? First of all, we can wonder whether a given result in algebraic topology depends on the chosen foundation, or would hold if we generalize to any other foundation that we know. Second, in order to formalize a proof in a proof assistant, we need to know how it works in type theory. And so given the result algebraic topology, can we understand how it would work in a type theory, and can we formalize it via a proof assistant? And to answer these questions, we need to understand a good kind of homotopy invariant foundation and develop algebraic topology in that setting. I should note this is not a new question. In particular, it was considered by Wygotsky, and there's an interesting story behind it. Right? So Wygotsky was working on motivic homotopy theory in the 90s, and he had this interesting result in 93 that was the basis for a bunch of other results by him and other people. But it turned out to be wrong, but 7 years later. And he could eventually fix it by proving a weaker result, but it was kind of an eye-opening experience that showed to Wygotsky the need to kind of bring proof formalization into the setting of homotopy invariant mathematics, and that motivated him to pursue the univalent foundations. Okay, so with this motivation in mind, let us look at a setting where this has already worked quite well, namely the non-homotopical setting, right? So there we have a foundation like set theory, which is the most familiar one. Then we also have elementary topos theory, which is the categorical foundations, and elementary topos is just some kind of category that axiomatizes the category of sets. And then we also have computational foundations, so type theory, and we can in fact effectively use this to formalize mathematical results. And notice, so I have given these references, not necessarily to like check every detail of this, but just to get a sense how long this took. And this is like a century-long development to really set up this kind of interaction between these foundations in the way that we have them now. So let's look at an example where this proof formalization in the non-homotopical setting has been used very effectively. And there's this recent example where Scholze proves a very kind of technical result in the setting of condensed mathematics, and he himself is unsure whether the proof is completely correct. And so kind of proposes the challenge to formalize this. And this was effectively done by a team of mathematicians, which includes Kevin Buzzard, Johan Commelin, and other people. And they used the proof assistant Lean and relied on dependent type theory to obtain this proof formalization. And this in some sense kind of provides a blueprint, right, for how things could work in more advanced mathematics and in more mathematics that involves kind of homotopy theory. So with this in mind, what we would like to have then is some kind of like analogous triangle, right, where you have a relation between now homotopy type theory and elementary infinity topos theory and so on. But of course, the reality is not that advanced yet. Rather, we do have a well-understood notion of homotopy type theory, and we have models for that, results. We do already have a notion of elementary infinity topos, which has been the focus of my works, starting with my thesis. And there's some comparison results between those two, but not the kind of strong results we have for the non-homotopical setting. And so all the work here is a progress to get a better understanding. Let me illustrate in one example how this can work. This kind of setting of generalizing results can work, and I will focus on the Blakers-Massey theorem. So remember, the Blakers-Massey theorem states that if a map F is n-connected and a map G is m-connected, then this gap map from the A to the pullback is n plus m connected. So now the question we can ask is, does this depend on any kind of specific property about the set theory or the spaces we used, or can we generalize this to alternative foundations? Can we formalize this with a proof assistant? All of these kind of questions. And the answer is yes. And there's a kind of nice web of results that start with the classical one and then generalize it in the first step to presentable infinity topos, and then generalizes to the full kind of arbitrary foundations, both in the elementary infinity topos setting, but also homotopy type theory setting, where it has been in fact formalized using ACTA. And I would have liked to kind of go step by step how each step generalized the previous one, but in the interest of time, let me just skip to the last one. And for this, I need to review the notion of a modality. So one kind of key step was to realize that there's nothing specific about n-connected maps that was used in Blakers-Massey, beyond the fact that it is a part of a factorization system. So we can factor any map of spaces into an n-truncated map followed by an n-connected map, and n-connected maps are stable by pullback. And this property of a factorization system is called being a modality. And so the result that we now obtain is that if E is an elementary infinity topos and LR is any modality, it could be n-truncated, n-connected, it could be something else, then if the pusher product of these diagonal maps of F and G is in the left class, then so is the gap map. So this pusher product does look unusual, and here it helps to remember that it really just, the fiber in this category of spaces is simply the join of the loop spaces. And this has already featured very prominently in the classical proof of Blakers-Massey and also other generalization in the setting of spaces. So in some sense, this pusher product of the diagonals is a parametrized version of this join. And this is was an insight of Anel, Biedermann, Finster, and Joyal to kind of really start using this pusher product very prominently in their approach, which is what I adapted as well. Another aspect of the work of Anel, Biedermann, Finster, and Joyal is to recognize really that it is the descent property that is the key input that is necessary to prove the result. And that's kind of an interesting, I would say, application of mathematical foundations, because descent was already known since the 70s to hold for spaces, but it is kind of their work that recognized that this is the one property you need to prove Blakers-Massey, and the rest, the other aspects of spaces, were not really necessary and could be removed. All right, let me also mention some future directions that one can pursue from here. And I will focus here on two future directions that both rely on the fact that in alternative foundations, one can have additional natural numbers. So the first one is the recognition principle, right? So recall the recognition principle states that E infinity groups coincide with infinite loop spaces. And if you think about it, both of those really depend on the notion of natural numbers, right? So an infinite loop space, in particular, requires spectra, and spectra are z-indexed, are indexed by the integers, and so they depend on the natural numbers themselves. Similarly, any notion of algebra or an opera depends on natural numbers. So we could ask ourselves, do they still hold? If we generalize to this alternative foundations. And the preliminary understanding on this is yes, but because in some sense they change in a kind of compatible manner, but it still needs to have a formal proof. Another example is Serre's finiteness theorem, which states very precisely when the homotopy groups of spheres are infinite. And again, we can ask ourselves, okay, if we have an additional homotopy groups and additional spheres, do we still have the kind of finiteness results that we get from Serre's finiteness result? And here I'm far more skeptical. So at least the preliminary understanding suggests that this might actually not be true. And further analysis is definitely necessary. And with that, here's my website and my email in case you want to know more about me or have any questions. And I'm happy to talk with you and answer any questions you might have.